Okay. There's a lot in this particular section that we're going to have to cover. It's the introduction of enthalpy. Okay, and really what enthalpy is heat content or heat transfer, but it needs to be under constant pressure. I'm not going to go super crazy into why the constant pressure is important, but it has to do with caloriters, and you just need to maintain the pressure. And it also works out nice because we're pretty relatively under constant pressure at all times at sea level, because the atmospheric pressure doesn't change much from second to second, much less from day to day. So it's close enough to kind of assume we're always under constant pressure. What's the state function?
I think that's only the beginning and the end.
Okay, so it doesn't depend on the path. All right. Internal energy, E. Pressure and volume are all state functions. So what do you think enthalpy is? A state function. And you can recall this because if you remember an equation we did quite often last year was like H products minus H reactants, or when we did Hess's law, lock it in, baby. You remember that? You don't remember that? You do not remember that. All the things. You don't remember what it was about. Okay? So this is a state function. So it doesn't depend on how you got there. It just depends on the beginning and the ending. Just so quickly show you here how we get this equation and how we know it's heat at constant pressure. So there's your Q. That is under constant pressure. When we do internal energy problems, I never put a sub P with it, but it is an assumed constant pressure. Then if I take the work equation, which we know is what? What does our work equation equal? And I plug it in.
Force times traction.
What is it? Negative B change in B. Right?
Yeah.
Well, we had the work as force times distance, and then we inputted it for, because most of the time what we're going to deal with for gases is a pressure-volume relationship. Okay? Now, it doesn't have to be a gas for it to be a pressure-volume relationship, but we a lot of times will do that. Okay? Now, if I manipulate this, so if I change Q and E around, that was an awful What in the world is that? We got all these negatives here. Alright? And we can just get rid of those negatives. So heat under constant pressure is change in E minus P change in V. And so you could say that is equal to that. See it? So change in H is equal to QP. So enthalpy is really just heat content under constant pressure. Alright? So you should recall this equation. Ooh. I'm hoping we did this a lot, so I'm assuming that at least looks familiar.
Oh, yeah.
Okay? If you remember, because it's a state function, we had in the back of our books a really big data table where we went and we got all the enthalpy of formation values from there and we plugged it in, and it really was just more tedious than it was difficult. Okay? At constant pressure, where only PV work is allowed, the change in enthalpy is essentially equal to the energy flow in or out of a system as heat. So if we say, let me see if this is on the next slide. Okay, yep. So if we said that heat is essentially the same thing as enthalpy in the context, if we're under constant pressure, then the sign conventions we use for heat also agree with the sign conventions we use for enthalpy. So a positive change in H means endothermic, and a negative change in H means exothermic. And we're going to get to those energy diagrams that we did last year, and the one that I showed you yesterday, quite a bit in, not today, but in the next couple days. So, questions so far on any of this stuff? Or indifferent? Okay, let's do this problem. This type of problem will be on your test, and it most often gets overlooked and messed up from previous tests that I've been seeing from students. Probably because we don't do it any time after today, much, at least this type of problem. And we do much more difficult problems that take a lot more thinking, that this easy one gets forgotten and messed up on a test. Okay, so just note that this is, you might want to make yourself a little note. Don't forget, I mean, this stuff is going to be on the test. Okay? It says when I got 1 mole of methane, burned at constant pressure, 890 kilojoules of energy is released. So I could say 1 mole of CH4 gives off 890 kilojoules, and I should probably do what with that number? No. There's a really important word up there that should tell you something.
Negative.
Yes. Okay, released. All right, just calculate the change in H for the process in which 5.8 grams of the sample of methane is burned under constant pressure. Well, we know if I got a mole, this is how much. What if I don't have a mole? Okay, so you're really kind of just doing stoichiometry here. You would convert that to what? And you use your unit conversion here to finish. So take that guy, convert to moles, and then use this as a conversion factor to figure out how much energy we released if I don't have a mole, because I'm assuming that 5.8 is short of a mole.
Yeah, because it's 16.05 grams.
So I'm guessing it'll probably be about a third of that.
I don't know.
Looking at the mass ratio, it'd say about a third of that, so what, 300 about? 320? For sig figs, 2 sig figs, is that right? And then you kilojoules. Okay, these problems aren't overly difficult, are they? Okay, but I'm telling you now, we get to much more difficult problems later, and the kids tend to focus on those more difficult ones, and then the easy ones become difficult because they just don't remember how to do the easy ones. Does that make sense? Okay? All right, moving on. Vocab City here for a while. Well, thought there was. Oh, it's on 2 different slides. Okay, calorimeter. I don't know what you remember about a calorimeter. Once it got to the end of the year, I'm not sure how much we were really paying attention anyways. But what a calorimeter is, it's used to figure out or measure heat flow. So let me show you kind of what it is. It's this chamber. And And usually there's an inner layer and an outer layer. Like this is usually just filled with air, or is used as air. Does anyone know why that might be air? Probably not.
Constant pressure.
That certainly helps. But if we're measuring heat flow, one of the best insulators is air.
Yeah.
We don't want we're trying to figure out heat flow within a calorimeter. So say that's a liquid, let's say it's H2O, because it typically is. Okay, if we are trying to figure out heat flow by placing something in a calorimeter, I don't want energy to be leaving the system before I can figure out how much energy was transferred. Does that make sense?
Yeah.
So this is kind of a dumb example, but it works. You should remember this equation. Your book gives it like something a little odd. It's like QSM change in T, and so their S is what I would call CSP. If you remember what CSP is, it's the specific heat capacity, which we'll define here in a sec and review that. Okay, but here's what's happened. Let's say I have water in here. All right. Could I figure out the mass of the water? Is it possible for me to be able to determine the mass of the water? Yeah, probably before I put it in there, but yeah. Could I figure out the temperature of the water?
Yeah.
And this is just a constant. So do I know everything about my water? For the most part. I don't know heat yet because I'm not doing anything. Okay, let's say I take a rock that's really hot and I put it in there. Okay? Well, could I measure the mass of the rock? Could I figure out the change in temperature before I put it in and after I put it in?
Yeah.
Okay? If I know the specific heat capacity, could I figure out heat transfer?
Yeah.
Or if I know the heat transfer, could I figure out an unknown variable? I want to make this very, very clear. Let's say I put the rock was out here and it was really, really hot, and then I put it in the water. What's going to happen? The water's going to warm up until their temperatures reach what? Equilibrium. Okay? Well, let's be very, very clear, assuming that this is well insulated and it's a material that's not a very good conductor of heat. Could you say that most, if not all, of the heat from the rock went where? Where'd it go?
To the water.
To the water. Okay? So if you know the heat transferred out of the rock, it would be the same amount of heat received by the what? Water. Okay, this is very, very important because there is going to be a homework problem in your notes that I'm not going to go over where you're going to solve for Q. And it's going to be, let's say, 2100 joules. Okay? Well, that's how much joules the rock gave off. Well, then it would be, so the rock gave off would make it negative, let's say that. Then the amount of joules the water gained would be what? But it would be positive due to direction, right? Does that make sense? So then you would take your answer from the first Q problem you did and say you didn't know CSP, but you knew M and you knew change in T. Could you then solve for the specific heat capacity of your unknown substance or something along those lines? Okay. Because I'm not going to go through a problem like that today, but you might see one. I think you're going to see at least one on your homework. Okay, so essentially what this does is it uses properties that we can actually measure and determine and allows us to be able to figure out some things from a heat transfer standpoint or from a specific heat standpoint that we do not know. Right? So, let's continue on here with 3 different types of heat capacities. Okay, this is the most important, just telling you now. Okay? The one we're going to use the most by far. You will use this sometimes. And this is probably the least, but that doesn't mean you don't, know what it is. Okay? The reason why this is most important is because if I just look at this, it says the amount of energy required to raise the temperature of an object by 1 degree Celsius. Well, we know that it takes twice as much energy to raise 2 grams as it does 1 gram, correct? And so mass is pretty important when trying to discover or figure out how much temperature will change, yes? Does that make sense? Okay. This is not temperature, or this is not mass dependent. So it tells you a little bit, but it just tells you the overall amount. Doesn't tell you anything about per gram. This one's very important because technically your units for this is a joule per gram times degrees Celsius is typically the units that you want. If they're not in that, you need to get it in that. So this is one of the rare things where if you get kilojoules, you've got to convert to joules. Okay, because it says how much joule energy do I need to raise 1 gram of a particular object 1 degree Celsius. This is also another interesting one that they don't use Kelvin, they use Celsius. And I'm not sure why they do that. Maybe so it's not as big of a number. That would be my only guess. So the only difference between this one and this one is what do you think from a unit standpoint?
Or just that one's joule per mole degrees.
So all they did is just did a molar mass difference. Okay? So this is how much energy per gram, this would be how much energy per mole. Okay? This is the one we're going to use the most. This is the one that's in that Q equation. Alright? So let me ask you, if I say water has a really high specific heat and aluminum has a really low specific heat, what does that tell you about the properties of those particular objects?
Aluminum would heat up quickly, but also cool down very quickly.
Okay. And water would?
Those things slowly.
Okay. So let's say if I know this is the specific heat of water. And I don't know the specific heat of many of the other things. Water's used so much. Let's say that's, I don't know, steel. Okay? To get steel to raise 1 degree Celsius per gram, I only need 0.21 joules. So it's going to heat up relatively quickly, right?
Yeah.
Water takes a lot more energy to heat up or to change its Celsius degree. So therefore, you would say that water takes a lot more energy or heats up a lot slower than something with a low specific heat. Like metals are typically low specific heat just because we know they naturally heat up really easily and really quickly. But he is also right, it also cools down equally as quickly. Okay? It's not just one direction, it goes both ways. Okay? Here's the problem. A little bit of a challenging problem here, but we'll get through it. All right, so going back to some mixing stuff. Okay, I will state this is something you probably don't remember from regular chemistry. There's your acid, there's your base. What's really reacting in an acid-base reaction is the hydrogen from the acid is reacting with the hydroxide from the base, producing what? Water. That's really your chemical reaction that's going on here. Okay? Just so just a little review here. So we're going to need this equation. And let's see what information they gave us. Okay, we're mixing two things. Okay? After the reactants are mixed by stirring, the temperature is observed to increase to 31.9 degrees. So we can probably figure out what the change in temperature is. Final minus initial. Final would be what? What was the initial temperature of both? So our change is what, 6.9? Okay, so essentially they're taking these two different mixtures, mixing them together in a calorimeter, and seeing what happens. Right? Got a temperature increase, okay? This says that the calorimeter doesn't lose much of the heat that you are trying to calculate. Gives us a specific heat capacity of water. Okay, gives us the density of our final solution. calculate the enthalpy change, okay, in, enthalpy change per mole. Okay.
What's the bottom for
1.0 grams per milliliter is the density. Okay, that'll come important here in a little bit. What I think is probably the most valuable right now is defining the heat transfer. Okay, we know the specific heat capacity, we know the change in temperature, we don't directly know the mass of my solution. Okay, but we do know that I took 50 milliliters and 50 milliliters, added them together, and I do know the density of that particular solution. Does that make sense? So I know that I have 100 milliliters. Does that make sense how I got the total volume there? Okay? And I know the density of this particular solution, which is 1 gram for every 1 milliliter. So I got a 100 gram sample. Does that make sense how I use density to figure out mass when I had volume? So here's essentially what's happening, guys. This acid and base is dissolved in water. Okay? When a reaction occurs in water, it appeared that the reaction was exothermic. Why do I say that?
Positive change.
Okay? Well, sure. Okay? It's positive change in T, but think about it. What is the surroundings in the context of this particular reaction? The reaction's done in what? Water. So what's the surroundings? Water. Okay? Water's temperature went up, which meant that the surroundings had to have gained energy. Well, where did the energy come from? From the exothermic reaction that was within the water. Does that make sense? Okay? So we can say right off the bat this guy's going to be an exothermic reaction simply because the surroundings in this context gained energy and saw an increase in temperature. So we're going to figure out the energy of the reaction by figuring out the energy that was received by the what? Water. Because the energy received by the water came from where? The reaction. Okay? And we know how much energy it takes to raise 1 gram of water 1 degree C. And we know that the change in the temperature of water was 6.9. So the amount of energy gained by the water was this. Okay, so that was the amount of energy gained by the water. Well, they didn't want to know the energy of the water, did they? They wanted to know calculate the enthalpy of the reaction that gave the energy to the water. Okay, so how much energy did the reaction give off? Negative 2.9 times 10 to the 3rd joules. And it wants to know enthalpy per mole, or remember we said enthalpy is really just heat, correct? So this is really enthalpy, but per nothing yet. So we need to figure out the moles of my stuff. Okay, so I can take joules per mole and get the enthalpy per mole. Make sense? Where do we get that mole number? This is where it becomes a little tricky. Here's the reaction. Everything's a 1-to-1 ratio. So I could take my volume there, right? I can convert that to liters. Then I can figure out how many moles per liter I have. Let me show you. I'm going to do it over here. I'm going to do it right here. So I have 50 milliliters. Now I'm going to say milliliters of my H plus here. Alright? I'm going to take and I'm going to convert that to liters. The reason why I'm going to convert that to liters I'll show you in a sec. 1 milliliter is 10 to the negative third liters. Following so far? Then I'm going to figure out how many moles of H plus I have using something we did 2 chapters ago. Concentration. Okay, I know that I have 1.0 moles of my H plus for every 1 liter. You're probably wondering where does all that stuff come from. Let me explain here. Okay, remember, isn't this the molarity of HCl? Well, doesn't HCl break up at a 1-to-1 ratio?
Yeah.
So if I know the moles of the HCl, what do I know the moles of? H plus. And since this is a 1-to-1 ratio, for the same amount of H plus I have, I need OH minus. So whether I figure out moles of this or moles of this, they should be the same, correct? Okay. I could have used this information to figure out OH minus and done the exact same thing, but they should be the same number in the end. That makes sense? Okay? That should give me the number I need to divide, which is 5.0 times 10 to the negative 2. Negative 5.8 times 10 to the 4th joules per mole. We could take that and convert it to kilojoules. Not 1 decimal place off. 58 kilojoules. Does it make sense? Sign convention here. The reaction gave off, because of the negative sign, 58 kilojoules for every mole. Does that make sense in the context of what happened to the water? Okay, the water gained the energy, the reaction gave it off. So we took energy that the water gained, worked backwards to figure out then that same amount of energy was given off by the reaction, but how much per mole? Okay, here's what we're going to do. We still have one problem that we didn't get to. So we're going to take another day tomorrow to finish. So I would recommend doing some of the problems you can do tonight. What you can't do, we'll finish the problem tomorrow and have an extended time to go over any problems that you're not understanding from your homework. Does that make sense? Okay, so then whatever you don't get done tonight would be homework then for tomorrow, but this will be the homework for today and tomorrow. Does that make sense?
Yeah. So what was supposed to be for tomorrow is this?
Yeah.
But try this on.
Yeah.
But don't.
Well, I'm not gonna be able to. I was just making sure that I didn't have to.
Wait, when are you giving your speech then?
Monday. She said that they're not gonna do it.
Oh, yeah, I remember that.
I actually haven't even started on
It started last night. It's having trouble finding it here. I'm trying to be. I'm doing $1 here, so I can find it the same in the Harrington law. It's like, oh, read books.